Okay, so what we move on to now in this presentation is how we actually interpret the wave function. We've seen that if you solve the Schrödinger equation for a simple system like a particle in a box, then you predict a number of different wave functions for the system having different energies. But what do these wave functions actually mean? And the person that gives us our interpretation of these wave functions is this person shown here, and he was called Max Born. He was a German scientist, and what he decided he would interpret, or you can interpret the wave function, was he decided that if you square the wave function, so you have a wave function psi, and you square that, what he said was that this represented the probability density of finding, or the value of that wave function squared represents the probability density of finding a particle at that particular point in space. Now, this idea came from the idea that if you have an electromagnetic radiation, so wave in the waveform, then the square of the amplitude of the wave is referred to as the intensity. So what Born suggested was that here you have a particle wave, and therefore the square of the wave function will give you the probability of finding the particle at that particular point in space. So what Born's interpretation is that you interpret the wave functions that come out from the solutions of the Schrödinger equation as probability amplitude functions. So if you again take a very simple system where you're moving along one direction, the x direction, and here's your point x, and now you go a small region of space, an infinitesimally small region, dx, then another way of stating this is that the square of the wave function times dx, and that now will correspond to the probability of finding that particle in a region x plus dx. So if you like, it's trying to find out, infinitesimally small region here, what's the probability of finding the particle in that particular region. So if we move down, then we can look at our solutions for the particle in a box that we did in a previous presentation. And let's take the first solution that we found. We found that we had psi 1 of x, and we had worked out that that was equal to some constant a sine of pi x all over L. Now, we had represented that function when we drew it. We were going from 0 to L, and we said that that represented like half a wavelength, and we gave it a positive amplitude. Now, what Born interpretation of that, to find out what it means and how to interpret it, and to interpret it in terms of a probability distribution, you would say that psi 1 of x, and now square it, and if you square that function, you're going to get a squared, and you're going to get sine squared pi x all over L. And now, if we roughly draw what that function would look like, again, it's going from 0 to L over here on the right. And what you'd find is that this narrows up a little bit. You'll find much more accurate representations of these if you go to your textbooks or your online resources that I've recommended. And again, square this time, and it'll be positive again. And what you're saying really is, if you go along, so your particle is going from 0 to L, what you can do is, if you pick off regions along here, so say you pick up this region here, Again, Born's interpretation says that the probability is the square of the wave function times this little area dx here. And then if you compare it down here to here in the middle of the box, another small region here, again dx, and let's again go to the same region here at the end of the box. Now what you note is that this magnitude here, this amplitude here, is larger than these pieces. So what this interpretation is telling us that if you have a particle moving back and forth here between 0 and L, in a classical description of that particle, the probability of finding the particle at any point along here is going to be the same as moving a constant velocity. However, what the wave mechanical interpretation is telling us is that the probability of finding the particle is highest here at the center of the box, and then it goes down gradually on each side. So that was for the first wave function that we for the particle in the box. Now if we move on to the second one, and again from our particle in the box presentation, we show that psi 2 of x is equal to a sine, and this time it's 2 pi x over L. So again, we plotted that from 0 to L. And what we found for this one was that it occupied one wavelength, so you had positive and a negative region, something like that, and that's positive and that's negative. Now if we go over here and we square that function, so that's psi 2 of x squared, that's equal to a squared sine squared 2 pi x all over L. So now if we plot that function, what we get when we square that function is we now get two positive bits. So the positive bit, if you like, from the unsquared function stays the same but narrows a bit, and now you have two positive values. So what that's telling us now for this is that the maximum probability of finding the particle is now at these two peaks here, if you like, a quarter way out of the box, a quarter way along the line, or 3/4 of the way along the line. And now what it's telling us here is in this region here, at that point there, you can see it goes to 0. What we've been told is the probability of finding the particle here, the probability density at that specific point, is 0. So in this small region here, it's very low. So it's different to what we saw for the first wave function, but again it contrasts completely with what we talk about classical behavior, where again if this particle is moving back and forth between these two points, then you would expect it to have a constant. The probability of finding that particle between the 2 points at any point between them should be the same. And likewise, then we can look at the third wave function that we solved for the particle in the box. So we call this psi 3, and again we found the last day, or the last part, the presentation on the particle in the box, so that was equal to 3 pi x all over L. And now of course our squared wave function is equal to a squared sine squared 3 pi x all over L. So again, if we drew out well, we did draw it out the last day, 0 to L, we now have 3 half wavelengths. So we go up like that, and something like that. So it's plus minus for the actual wave function. For the squared wave function, what we now get is let's draw it out here to make it quite reasonably accurate to look at. So we get 3 humps like that, if you like it. So this is 0 to L, and this is 0 to L here, and we'll just call them plus and plus again. So now you see, if we look at our probability, here we have highest probability at this point, and this point. And if we draw in regions, we have our highest probability regions here at the top of these peaks. And now we have two regions where the actual probability of finding the particle is predicted to be 0.